My name is Amgad. I'm an elite application engineer with Intercat here, and I will be your host for the next 30 minutes or so. We'll start with our agenda for today. So we're going through a SOLIDWORKS plastic introduction and licensing levels, cooling and warpage questions, why we need this tool, who should use this tool, and how to set up cooling and warpage study. First, SOLIDWORKS plastic license levels. As you may be using SOLIDWORKS already, so you know that we have 3 levels in SOLIDWORKS: standard, professional, and premium. It's the same here in SOLIDWORKS plastic. So we have the standard level, which only do flow analysis, and through this level you can do or test for the filling, short shot, you can do surface and mold and solid meshing. You can detect weld lines, air traps, and you can also test multiple gates. The next level up is plastic professional, where you can do flow and pack analysis, and you can have more extra tools like multi-cavity analysis. You can do runner balancing. You can detect the cooling time. You can also detect shrinkage and sink marks. You can do overmold, insert overmolding, gas assistance, co-injection, and fiber analysis. The last level up is SOLIDWORKS Premium, SOLIDWORKS Plastic Premium, where you can do the full cycle. So it is flow, pack, and cool, plus the warp analysis. Okay. So who should use this tool? Of course, it will be plastic part and tool designers. So if you are only a plastic part designer, you can use the standard or the professional license. If you are a tool designer, a mold maker, then you need the premium license. And this will take us to why we need to do cooling and warpage analysis. So the answer here is to get more accurate result by accounting for cooling system design. If you may have noticed that the standard and the professional license level assume a uniform cooling environment of the part and the mold. So it doesn't account for your cooling design, for your cooling system design. Okay. All right, so we will jump straight away here to the difference between applying or getting the result in the standard and the professional level and on the premium level. So by accounting for a uniform mold temperature, this is the result, the one on the left. The one on the right here is the accurate model temperature. This is the accurate model temperature at the end of cooling, of course. Again here, this is the temperature at the end of cooling, and you can see here, this is a uniform one, the uniform temperature distribution, and this one here is the accurate one which accounts for your cooling system. Going to the next result, this is a warp, this is a part warpage. Again, this is a uniform one, and you can see the difference here on the accurate one which accounts for the cooling system. Another important result, the warpage in the Y component. Again, can see the difference in the result, very obvious here. All right, so we need to answer the third question actually, which will be how easy or how we can set a cooling and warpage analysis. So this will be our time to jump on into SOLIDWORKS to see how we can do so. So if you may been introduced to SOLIDWORKS Plastic before, it's part of SOLIDWORKS, so you are working on the same environment, can benefit from modifying the part at any stage, can benefit from applying different configurations, and Plastic is no more than another add-in that you can use straight away inside the same SOLIDWORKS design environment. So we jump into the SOLIDWORKS Plastic tab, and as you can see, we have two options here to do solid or shell mesh. For if we are going to do cooling and warpage analysis, we must use the solid option, and we can use either an automatic or a manual mesh. I will go with a manual mesh so that we can see all the steps. So once you select the solid mesh and you have SOLIDWORKS premium license, SOLIDWORKS Plastic premium license, you have the option to account for the cooling system and also for the virtual mold generation. So we go to the next step. So SOLIDWORKS start recognizing the model, and we have here cooling channel design, runners, or runner wizard. So we are going to use the cooling channels, and to define the cooling channels, we just need to select the sketches that are forming them. So these sketches are created previously in the model environment, in the modeling environment, and here we can specify the type of channel, whether it is general, buffle, or bubbler. So this one will be general. I can specify here the cooling pipe diameter and the element count. The more element count the more accurate your result will be. Okay, so this is the first stage here, defining the general cooling pipe. Then we will jump and define the normal one, which is a bubbler, a buffle. Again, the same diameter, and I will assign that, and you can see here the difference in color to show you that this part of your cooling system is not a general one, it is a buffle. Going to the next step, we can define our virtual mold here by either coordinate or by size. So we'll use the size option, can use the standard values here. So I will have 300 for the X direction, 120 for the Y direction, and 220 for the Z direction. Add the mold, and let us go to the next step. As you can see here, SOLIDWORKS recognize 3 domains. So one for the cavity, one for the cooling channel, and one for the mold. Okay, going to the next step. Next step, here we can define the mesh size. So how accurate your result will be is based on the definition of the mesh size. I can have a uniform mesh size, or I can type here, for instance, 15 for the size of the mesh, and get SOLIDWORKS to automatically recognize the small fillets and small features in my model, and it will automatically create the suitable size for this model. So I will go mesh. As you can see here, the small features are being covered based on the auto refinement option. All right, so this is the mesh for the cavity. I can jump straight away to the mold, and again here I can specify the mesh size, and I will create a mesh. As you can see, it's instantaneously creating the mesh for me. Let's go to the next step. Next step is a summary here saying that my mesh is waterproof. This means there is no gaps, there is no voids, there is no silver faces in my mesh. It is all good to go. And this is a percentage of the bad elements, and this is a percentage of the very bad elements. The maximum aspect ratio, it is a little bit high here, but it's just for the demo sake. I can, of course, specify smaller mesh size in the setup and get a better aspect ratio in my mesh. So I will accept this. Go to the next step here. This step here, I can control my mesh and add more nodes for on this area that I want to get more accurate result by inserting nodes or adjusting nodes or merging nodes. So it gives you more control over your mesh to make sure that you are getting a more accurate result. Okay, so I'm going to accept this one. You have two options here to use a tetrahedral or hexahedral mesh. It depends on your part geometry. So a tetrahedral mesh will cover better the parts with more fillets and curvy surfaces, while the hexahedral one will cover the more prismatic part. So I can jump straight forward to the next step. So here is the transition from the surface mesh to the solid mesh. So I will go straight forward. I can change the smoothness of the transition. So this is creating a hybrid tetrahedral mesh, as you can see here, with two levels from each side of my cavity. Right, then I will go and create the mesh for the 3D mesh for the mold. Again, very quick, creating the mesh, and you can see here the transition and the smoothness of the mesh from the cooling channel to the virtual mold to the cavity. Okay, so it's all compatible mesh here. Go to the next level. We have nearly finished the setup for the mesh, and we are ready to go to the next step. So as you may, if you are already a SOLIDWORKS plastic user, you may be introduced to this part of the setup. So first we need to access the material database that we are going to use for the cavity. So as you can see here, we have more than 500,000 of commercial plastics material. You can sort them by family or by company. You can search. You can add your own material as well. I will use an ABS generic material here for the polymer. For the cooling, again, I have another database for the cooling fluid. So I can select from this. We have 39 commercial coolants. I will just select water for this one. And next, I will add a material for the virtual mold. Again, we have more than 185 materials that we can select from. Again, you can create your own material and add them to your user-defined database. Okay, so accept this setup. As you can see, once you accept step, you will find that there is a green tick showing you that you have successfully completed this step. We're going to jump into the process parameters, and you can see here we have filling the fill setting. So automatically the melt temperature and the mold temperature have been transferred from the material property to your filling setup. The injection pressure as well. You have full control of changing this, but these values here are automatically mapped. You can also change the filling time. Again, we have a green tick here on this step. On the next step is the packing, pack settings, and again you have the option to automatically use the option from SOLIDWORKS, or you can input the pressure holding time based on your system and pure cooling time. Okay, so our settings is very easy. Just need to input the ambient temperature and the gravity direction, right? And the cooling setup, this is another part that you need your attention. So here again, the inlet melt temperature of the material is automatically detected. The ambient temperature, you can add here or modify your ambient temperature. This is the minimum cooling temperature. You can control the average flow rate of your coolant. The mold open time can be defined as well here. The ejection temperature, so our material solidified at 90 degrees. So this will be our ejection temperature, and again, all these parameters have been developed and transferred from your material properties into your cooling setup. Okay, the last thing that we need to set up here, or to modify if you would like, is inlet and outlet directions. So you can reverse the inlet and the outlet direction. You can override the default coolant in one branch of your cooling system if you would like. Can also override the inlet temperature. For instance, I will override this inlet temperature here. You can override the flow rate that you already set up in the previous step. And this is only for this branch, while other branches are still on the same inlet and flow rate. So it depends again upon your system and upon your design and how complex is your cooling system. Again, once you accept this, you have green tick here showing you that you have completed this step. Before we go and set the model for setup, for running, we need to include the injection or define the injection location. So I can use SOLIDWORKS logic here for automatically adding an injection location. As you can see, it's automatically selecting this location for the injection point. You can just say add, or I can manually define this based on my experience with the mold design. So maybe I select this point for instance and add it. Yep, so we finished. Actually, I don't want to add it here. I want to add it here. Yep, perfect. Adding the injection location. I'm all ready now to set my analysis to run. So the best way here, as you can see, we have we can run a flow analysis, we can run flow and back, and we can run cooling flow and back. Can also use my batch manager here to define the way that I want my cycle to run. So I can go here straight forward to my study and selecting my current analysis here. Can delete all the above setup. Can delete it. Delete this one. And delete this one as well. This one. And I can define my cycle by running a flow. Sorry, should be flow and back. So we'll delete this one and we'll start with flow, then cooling, then flow and back, then again cooling and warp analysis. Once you have this setup, you can set the model to run immediately, or you can set it to run maybe after hours to utilize your license in a better way. Okay. All right. So this is how you set your model, and let us have a dynamic look on how the result will look like. So I will jump to another configuration here where I already solved the model. Right. Jumping into my results folder, and you can see we have flow results, we have back results, we have cooling and warpage results. We will be focusing on the cool and warp results. So we'll start with the cool first. This is loading the cooling results. And I have the options here to hide the cooling line, so I can see that the temperature distribution, or the first result here is the cooling part time. And you can see here it is 22 seconds. This is the maximum, and it's taking place at this location. You can see the average, the cycle average temperature, and temperature at the end of cool. And this is very important here because I want to see the parts of my model that still over 90 degrees using my ISO clipping here. Sorry, ISO surface mode. So you can see here all these parts or these regions in blue representing the volume that's not solidified yet, or the value between 90 and 130 degrees. Okay. We're still looking into the cooling results, and one of the the most important results here is heat flux in the cooling system. So I can turn here the heat flux, and can turn the ISO surfacing and set my minimum. This is a heat flux. Set my minimum to 0 to see how my cooling system is working, how much heat it is absorbing from the system. So this is showing me if my cooling design system is working or not. Next, we will be jumping into the warp results. So here I will turn off the cooling line and turn on my cavity visibility, and can see here the total stress and displacement as a result of the in-mold residual stresses. You can see here my shrink marks, my sink marks. profile. This is the in-mold residual stresses. Can change the scale here of the deformation, can play an animation. But this is the most important thing here, showing the warpage in my part as a result of the cooling system. When it takes into consideration, this is a deformed result. This is exaggerated or scaled up by 5 times. We scaled it by 2 times. You'll see the difference. And this is a scale 1 to 1. As you can see, the main geometry is the one that is transparent, and this is the geometry after ejecting the part. Okay, so last thing that I want to show you before ending this webinar is the report that's automatically generated by SOLIDWORKS Plastic. So this is this report here is automatically generated by SOLIDWORKS Plastic, and it shows you all what you need to include in a report that you may represent to your manager or your customer, showing the material properties, all the material properties and the results, the steps of setting up the model. As you can see, very informative report. It is like 55 pages of information, and it's just ready for your conclusion here. The report can be on a Word format, a PowerPoint, or an HTML format. Okay. I hope you find this webinar useful, and if you have any questions, please send them to my email that's on the screen here. It's amgad.jacob@intercad.com.au. Again, thank you for attending this webinar, and see you next time.